Hi, this is Dr. G. Bailey, and this video will continue where we will talk about enzymes, which is topic 2.5. Here are some of the understanding application skills that we need to work on. The first thing we're going to learn about the enzymes, that it has an active site and that binds to specific substrates. We're going to talk about how enzymes are catalysts, involving things to go faster. We're going to talk about how enzymes can be actually denatured. Moreover, we're going to talk about different factors that can affect its speed and how he acts, right? His rate, in this case, will be temperature, pH, and substrate concentration. So we're going to talk about those threes and the graphs and everything about them. We're also going to talk about the industry, because we understand more of the enzymes, how we use that to be able to produce products that is beneficial for us. An example of that would be the lactose-free milk. We're also going to talk about how to design different types of tests, experiments in which we're testing the effect of the temperature, the pH, or the substrate on the enzymes. And the most important thing is we need to know how to do these techniques, right? Because one of the practicals is, again, if you are an SL student, there are 6 practicals that you need to know, and there's 7 for HL. And one of these practical is how to manipulate factors such as temperature, pH, or substrate concentration on how it affects a specific enzyme. So you have to do a kind of lab in which you're experimenting these stuff. So I kind of will talk a little bit of these in this video. So to start with everything, we need to know what is an enzyme made of. Now, an enzyme is actually made of proteins. We should know this from the topic 2.4, right? And their shape has everything to do with the function. It is their structure that will give out what their function are. That's very important. Now, they can break things or they can make things. A lot of students think the enzyme is only about breaking down, but that's not true. Enzymes can also put things together, so it's either way, making or breaking things. Now, when we say enzyme is a catalyst, okay, that means it's actually speeding up the rate. That means it's speeding up the reaction. It's making it go faster. So for example, if you take a chemical reaction that takes an hour to do and you put an enzyme in there, it might do in 5 minutes. That's how fast an enzyme can speed up a reaction. Now the question is, how does an enzyme speed up reaction? It does that by lowering the activation energy, which I will explain more about this in the following slides. But for now, just remember that enzymes are catalysts, which that means they speed up the reaction by lowering the activation energy. Now here's a trick when it comes to test. All the enzymes in the end of the word it ends with an A's. So every time you see the word A's, automatically you should know it's an enzyme. Example, we have sucrase right here. It breaks sucrose, so it's sucrase. Maltase breaks maltose. So if you have lactase, that's my basic breakdown lactose. And nuclease is breaking nucleic acids. Now, there is exceptions like pepsin, which doesn't sound an A's, and that breaks down proteins in your stomach, but most of the enzymes, they end with the word A's, lactase, maltase, sucrase, and it keeps going. So in the test, if you have a multiple choice and they're asking for a certain enzyme, if you see the word A's in the end, you know it's exactly an enzyme. Now, all the enzymes, they have a 3D structure, so they are more like globular. Okay, and their structure is very important, like I said, because it's their structure that will give their functions. But when it comes to structure, we have to go back to 2.4. Remember that enzymes are made of chains of amino acids, and the sequence of those amino acids will tell you your structure. So as been here, underlined, is the specific chain of amino acids. The sequence of the amino acids will tell you the shape of this enzyme. And if you have the shape, you will know the action. So it's one thing leads to another. The sequence of amino acids will give you the shape, and you having the shape will give you the function. Okay? That's important because you might get this as a multiple choice. How do you lead to a function? Well, first you find the sequence of amino acids. Once you have that sequence, you're definitely going to know what's its structure. And once you know its structure, you will know what is its function. Okay? And that's how you separate different enzymes. It's according to its sequence of amino acids. Okay? Now, when we're talking about enzymes doing its work, it's binding to something. And that's what we call a reactant, a substrate. Okay, so the enzymes here is this green part here, right? Oops, let me get here with the black. So this green part here is the enzyme. Now this yellow right here is it's basically a substrate, okay? And it's basically, there's a typo here, but it's a substrate. Now, substrate is a reactant. That means it's the one that's starting the reaction. So the substrate will bind to the enzyme, and they become this enzyme substrate. I don't know why it's written subtract, but it's substrate complex. And eventually, after that, it turns into a product. As you can see, two pieces are coming out of the enzyme. Now, here's the most important thing, is that you need to know the word substrates and products. So for example, let's say A and B will make C. In this case, A and B, who are they? They are, oops, let me put here, they are the substrate. Not only do we say they are the substrate, I'll put it here, which makes more sense, substrate. Or if they're not a substrate, it's another word, we call it the reactant. Now, C, in this case, would be what? Would be the product. So, who does the enzymes bind to? The enzymes binds to the substrate. So the word substrate and reactant is the same thing anytime you find that in the test. Now, another important thing that we know that enzymes are binding to the substrate is the fact that the substrate has to have a specific shape that combines with that of the enzyme. So if you see here, look at the shape of the substrate, right? It is exactly the shape of the entrance of the enzyme. Now, what is this location in the enzyme? We call it the active site. So the active site has to have the same shape, right, as the substrate in order for them to match. It's like a key lock thing. So enzymes are very specific to the substrates. Not all the enzymes are going to do any kind of substrates, right? Because if they have a specific shape inside of them, that means they're binding only to a specific molecule. So that means they're very specific. I can only bind with you because you have my shape. You, on the other hand, you don't have my shape, so I'm not going to bind to you. So in what makes that determination? What tells you what kind of things you're going to bind? Look at active site. That means whatever is the shape of the active site, it is that way that you will know what is the substrate or the reactant that you're going to bind to. So it's all about the shape of the active site. He is the big decision here. He's the one who's going to tell you who do we bind to, because it's his shape that shows everything, okay? So with that in mind, when we talk about the active site, which is a part inside of the enzyme, right? It's where you see the shape that I'm drawing here of the enzyme. Now that shape, it has a certain chemical environment. That means it is the amino acids that you find in this bond here. Now, what made the shape? If I'm going to repeat this again many times, what that made that shape? It was the sequence of the amino acids. The sequence of the amino acids made them like that. If you had another sequence, maybe the enzyme will look like this. If you had another sequence, then maybe this would be the enzyme. If you have another sequence of amino acids, then you have something more like this. So each switch, it all depends on the sequence of the amino acids. So the shape here, as it means the shape here, it all depends on the sequence, as I said, of the amino acids. That tells you what kind of molecule will bind to the active site, because the active site has the same shape as the molecule that is going to bind to it. So let's look at the mechanism here, right? You have the substrate, right? In this case, substrate is the same thing as a reactant, right? And that substrate is going to bind inside. Now, if you look at the shape of the substrate, right, it's exactly the shape of the active site. This right here is the active site. So the substrate binds to the enzyme at the active site. That's what you write. The substrate binds to the enzyme at the active site, as the substrate has the same shape as the active site of the enzyme. Once the substrate binds to the enzyme, it becomes an enzyme substrate complex. You have to know this word, enzyme substrate complex. And it's very straight, right? It's the enzyme, the substrate, and they made a complex. They bound together. Once they form this complex, then the enzyme will create the product. And now you can see the two pieces coming out. These are basically the product. And the enzyme is still there to be reused again. So that's the mechanism of an enzyme. First, the substrate binds on the active site of the enzyme, it becomes a complex, and then eventually it releases the product and the enzyme is ready to be used again. So here is a way of writing that I put it here. You can always pause this video and write these words, but it's just showing you in words how to write this on a test. So enzymes have a complex 3D dimensional surface to which particle reactants called substrates fit like a hand in a glove. That's complicated. You can always say enzymes are 3D shape, right? And they bind to substrates like a hand in a glove or key to lock chain. When this happens, the enzyme and substrates bind tightly together, forming an enzyme-substrate complex. So you can just say an enzyme binds to a substrate, forming an enzyme-substrate complex. Okay? Don't worry about the rest. And then as a result, there's a chemical reaction. Of course, there's a chemical reaction in the active site, and then the product is formed, and then they free the product from the enzyme, and it goes back to work again. So when you're writing an enzyme thing, the first thing you mention is about how the substrate is going to attach to the active site of the enzyme, having them both the same shape. Once they bind, they become an enzyme substrate complex. There is a chemical reaction and turns the substrates into what? To products. And the product is released and the enzyme is ready to be used again. And it's important that you say that the enzyme is ready to be used again, because it's true. The enzyme, you can use it as many times as you want. He never gets tired. Okay? Now, here's important thing, hypothesis that they have, this thing called lock and key. They're basically saying that a substrate has to fit extremely perfectly well at the active site of the enzyme. So you know how there's always a key for a specific door, right? Because the key has a shape, and the door, of course, the way you put it inside, it has a shape too, right? So the key and the lock have to be exact. It's the same thing about the substrate and the enzymes. They have to be exact. So if they're exact, that means they're going to fit. And if they fit, you'll be able to produce a product from that reactant, right, or that substrate. And then eventually they will be released. And then again, the enzyme is free to go again and do the process all over again. So this is repeating it, but this is just hypothesis. Now, we know more. If you do HL, you will see that there's something called induced hypothesis, which it doesn't have to be exactly the same shape, but that's for HL students. Now we're just doing 2.5. In this case, we go with the lock and key hypothesis, which means the substrates have to have exactly the same shape as the active site of the enzyme. Otherwise, they will not bond. So right here, I'm going to give you an example of what enzymes really do. So let's just say I have this one person right here. He's in grade 9, right? And we have this girl right here, right? She's also in grade 9. Now, they basically are both shy people, right? And they are in the same classes, and somehow they do both have a crush on each other, but they're so shy they will never say. So eventually they never get to talk to each other. And then they get to grade 10, and when they get to grade 10, they're still in some classes together, right? They're still here, blah, blah, blah. But basically she joins the dance club, and him, in this case, he joins the football. But they don't talk to each other. Again, very shy. So they get to grade 11. And when they get to grade 11, they still have the same IB class with each other. But this time, they barely talk. They say hi, hi, but they don't say anything. She continues to dance. He continues to football. However, they get to grade 12, right? And in grade 12, what happens? They start talking to each other to study for the IB exams, and they eventually, have a study together in the library, and they start showing more affections, and eventually they start to date. And then they go to college together. If that's in real life, they go to university, and they get together for 3 years dating, and then they get married. Now, if I ask you, how long did it take for them to get married? That's 4 years in high school, plus another 3 years. That means it took them 7 years to get married, okay? Now, if I change the story, if I decide to put another person in the middle right here, okay? And that person comes in the grade 9, he's like the most talkative kid in the class, and he's always socializing. So he goes and sits one day with this guy, opens him up, and he says that he likes this girl, and then the next day he sits with this girl, and she opens up and says about him. Because this guy is, I don't know, he's very trusting and he's very understanding and he can easily make people speak up. So he figure out that they both like each other. So he creates a party. So he creates a party at his house. And in that party, he drags those two by mistake. Well, mistake, no, it was planned by him. And he puts them in the bathroom and locks the door. So he forces the two of them inside the bathroom to stop being shy and talking to each other. And guess what? Right after that, 2 hours later, they were actually dating. Now, they dated throughout the entire school and then they got married soon as they got to university. Okay, that's crazy. I know this doesn't happen in real life, but let's just say here, what happened? How long did it take for them to get married? Since they're married on the first year of university. It literally took them about 4 years, right? That's the whole point here that we want to try to say, is this guy right here, the middle guy. Who is he in science? Science. This guy in the middle, he was the catalyst. And what I mean by catalyst, it means he speed up the whole dating process between the two. Without him, it literally took them 7 years. I mean, it took 4 years from them to start dating and then 7 years to get married. But because I put a catalyst, which was this boy right here in the middle, they start dating in what? In less than a week of school, less than a week, and they got married in 4 years. So imagine 1 week, right, compared to 4 years to start dating. That's a lot of time. And all of that because this one guy here in the middle was the catalyst. He just speed up the reaction. What did he do? He connected the substrates. He connected the reactants. He brought them closer. That's exactly the job of an enzyme. That's what enzymes do. So the enzymes, they're like catalysts. They pick up these substrates that are out there and put them together faster. For example, let's say that this is a box right here, and we have substrates. Now the substrates are moving, but they're moving very slow, okay? And the only time that they become a product is when the substrate hits with another substrate. When they hit each other, they become a product, okay? So they have to hit each other. Now imagine them moving slowly and they're moving in different directions. How long will it take before these guys hit each other? We don't know. It might take days before they hit each other, right? If I put temperature, if I increase the temperature here, yes, it's going to get hot. What happens? They're going to start moving more faster. So the chances of them colliding, it is even higher, right? But it might still take another day. Like instead of being 3 days, it might be 1 day. Now, here's an even better process. The better process is if I don't add temperature, but what I do is I add enzyme. If you add an enzyme here, let's put in another color. Let's put it in blue. If I add an enzyme, the enzyme, think of an impatient person. He's just like, you know what? I'm not going to wait for them to bump into each other. I'm just going to pick you up and move you here and bump you too. And voila, you made a product. And then the enzyme goes and jumps and pick up this guy and moves him here and bump with this guy and makes another one. And jumps here, picks another guy and makes it. So the enzyme, what it does is it speed up that reaction by bringing the molecules closer to each other and reacting. So that's the job of the enzyme, is just to speed up the reaction. Now, because we did that, we have to go and talk a little bit about the activation energy. So imagine here, that box, right? You have a molecule here. Jesus, they need to connect to each other. But for them to connect, what they have to do, they have to move. And God knows how long they will keep moving until they will find each other. But they might just miss out each other and they just keep moving. While they're moving, what are they doing? They are using their energy, right? So they're wasting a lot of their energy and they need a lot of energy to keep up moving until eventually, poof, they hit each other. So you're using a lot of energy to meet the two of them. Now, that is without an enzyme, using a lot of energy. But what if I come in here and I drop an enzyme, right? The enzyme does this. He picks him up, he drags him here, and voila. And then what he causes a product. Now, how much energy did you use here? Practically almost nothing, right? Because the enzyme came here, picked you up, and dragged you here, and joined you with this guy. So less energy was used to put those two together because the enzyme kind of saved that energy. The enzyme kind of says, you know what? Why would you move so much, bouncing all around until you collide this guy when I can just take you there and connect you with him? So that's the point of an enzyme, is just to speed it up and to reduce the amount of energy. So once again, the enzyme, what it did was it reduced the amount of energy needed to make the reaction happen. Right? So it reduced the amount of energy needed to make the reaction happen. Now, what do we call this thing? The amount of energy needed to make the reaction happen. The amount of energy needed to make the reaction happen is known as the activation energy. Now you're kind of getting it, right? Oh, so activation energy just saying is how much energy I need in order to collide these two. Well, in the box with no enzyme, what happened, you needed a lot of activation energy. You need a lot of energy to put them together, right? But in a box where you have the particles and the enzyme, you needed less energy. So that's what the enzyme did. It reduced what? It reduced the activation energy, the amount of energy needed for them to react, to get the reaction going on. So with that in mind, basically the enzyme has two things, right? One, it's saving some energy, and second, it's speeding up the reaction. So you have to remember these two little things. One, it saves time, right? And it saves energy. These are the two main things that the enzyme is doing when it's connecting these substrates to make a product. Now, since we're talking about making reaction go faster, like I said, we can increase the temperature and make the molecules move faster, right? But they will be faster. They might collide. But if you keep increasing the temperature, what happens when we increase the temperature too much? It can destroy the molecules, right? Like imagine our temperature is at 36 and let's increase it to 40 to make our reaction go faster. Yeah, but if you do that, goodbye. You're dead. Go to the hospital. So we can't do that. So instead of raising our temperature, it's much easier giving us enzymes, right? This is why we say the enzymes can increase the rate of reaction without increasing the temperature. It's like, hey, dude, I'm going to save your temperature. Keep your temperature 36. Let's just put enzymes in there and it will do the work, okay? And it does this by lowering the activation rate. So the activation energy, which that means it takes a shortcut pathway. Like I can make this thing go faster without raising the temperature. Now that you understand a little bit of the activation energy, now you have to know how to graph it. And here is the graph that you have to know how to draw it because this graph will show up in IB exams. So on the y-axis here, you can see it's the energy, right? The energy that they need. And here is the reaction that is coordinating. That means it's happening. Why? Because right here, at this point, we have the reactants, as you can see. And this point right here, we have the products. So the reaction is going in this way. Reactants are becoming products. Now, here is the amount of energy that you need. So you can see that it's not zero, it's up here because every reactant already has a certain potential of energy. Now, he has this much energy, but he has to move a little bit more in order to reach the energy that will hit with the other molecule. So that is how much energy, right here, that these substrates, these reactants need in order to bounce to each other. Transition stage means the moment they bounce to each other and they start to react. So in this energy here, right, that's the activation energy, how much energy the substrates or the reactants need to react. So here is where they react and then eventually they flow and produce products. Of course, there is a release of energy as you go down after the reaction. So the graph would be looking something like this. Reactants are here, they need some energy, and then boom, they go down. Okay, that's a normal reaction of substrates without enzymes. So what happens when you actually put an enzyme? So here is a picture. You still have here, let's put it in black. here is the energy, right? And here is the reaction. And here you usually will have the reactant. And here you will have the product. Now, there's two pathways, the long pathway, the short pathway, right? The long pathway is the big mountain here. The big mountain here is basically saying that you need this amount of energy, or should I say activation energy, to make the reaction happen. Now, the bottom one here, you see that there is only this amount, right? So what happens? Which one of these lines is the enzyme? Because this is the first line that we have, right? And then we have the second line, which is this, it's smaller. So looking from this, you can see that this one, you need less energy, and this one, you need a lot more energy. So when we put an enzyme, it means it needs less energy. So this lower mountain here, there's an enzyme. This one has no enzyme. So whenever you don't have an enzyme, you have a bigger activation energy. And if you do have an enzyme, you have a lower activation. That's what it is. So let me just go here and make sure if I had to draw this, let me put it in a place here where, let's use here. So let's just say if they give you in the test, okay, they give you a picture like this, right? This exact picture right here. And they say, if you had to add an enzyme, how would this picture look like right now? You will put the same thing, right? Because the enzyme, the reactants always have the same amount of energy in the beginning. But then you will have a smaller mountain and then it connects down. That smaller mountain right here, this was an addition of an enzyme. So you would just add that smaller mountain under the bigger mountain. That will show a lower activation energy, and that will show the addition of an enzyme. So that's what you would do in a test, okay? Now let's talk about the factors affecting the enzymes. That means, what are the things that can make the enzymes work even more faster, or what can stop the enzymes from working, okay? So we have three: substrate concentration, the pH, and the temperature. And you can see pH and the temperature, right? These two, if you remember the proteins, they affect the proteins. Well, guess what? Enzymes are proteins, so these two should be very common to you. Substrate should be something brand new to you. So all of them will affect the enzyme catalyst reaction. And of course, depending on what you do, you might denature them. That means you might destroy the shape of the enzyme. So we're going to explain more about this when we talk about each of these factors here, okay? So let's start with the temperature. What does the temperature do to an enzyme? Now, first we know that the more temperature there is, the more collisions, right? Why? Because if you put temperatures on those substrates, like I told you in the box, if you put two molecules here and you increase the temperature, yeah, they're going to move faster and they might hit each other. Great. Even the enzymes, they might move faster. But most of the enzymes, when I say optimum, and you have to use that word on an assay, remember optimum, always use the word optimum in your assays. When you say there's an optimum temperature, let's say it's about 30, right? Now, if you put that enzyme, that his best temperature is at 30, that means when his best work is at 30, and you put him in the temperature of 70, you completely destroyed, in another word, you denatured the enzyme, so it won't work, right? So temperature is good. It can start making them move faster, but if you go up beyond a certain point, you will kill it. So this is what a graph of a temperature would look like. In the beginning, right here you see there's the enzyme activity on the Y, right? How much the enzyme is moving. And here you have the temperature. So you always put on the x-axis the factors, right? So the temperature is rising this way. It's becoming 10, 20, 30, it's rising. And the activity of the enzyme is rising. Now, if the temperature is rising, so is the activity of the enzyme. Yeah, great. So the temperature is making the enzyme move a little bit faster. Totally cool, no problem. They're starting to work more because the enzyme and the temperature are working together. More temperature, enzymes are working faster. But eventually, here, it says that the optimum is right here at 40. That means the best temperature for that enzyme to work at its best rate. So up to here, the enzyme was working great. It was increasing as the temperature was increasing. So the enzyme is acting faster, is working faster as the temperature. Up to 40. After 40, the enzyme starts to not work faster. It starts to drop very fast. What's the reason? The reason for that is because the temperature has gone beyond 40, and that means now the temperature is destroying the enzyme. It's denaturing the enzyme. So if you had to graph this in a test, of course you put the activity of the enzyme here, and you put the temperature right here, and then the most important, put of course the units, and then you have to make it look like they're going like this, and then you have a sudden drop. If you draw a graph that it makes like a mountain, you're not going to get the points, because it's not like it's slowly increasing and then slowly decreasing. That's not true. What has to happen is there has to be a sudden drop, because after a certain point, the temperature destroys the enzyme. So it's not slowly dying, it just completely fastly dies. So this is the right way of drawing the graph on the test. And many students make the mistake of drawing this one, making it like a mountain that is perfect shape. It's not true. It does rise slowly, but then it cuts down very fast. And that's how you're supposed to draw it. The next one is the effect of pH. Now, we know also that extreme levels of pH will denature the enzyme, right? Because again, what happens? The amino acids, they're losing their charges. They're being destroyed. Some of the positive becomes negative, or negative becomes neutral. So we have different enzymes, and enzymes have different favors. Like each one has their own type of pH. Right here we have 3 types of enzymes. We have pepsin, we have salivary amylase, and arginase. These are 3 different of enzymes. And it doesn't mean all enzymes work at the same pH. They all have their preference. So for example, pepsin, he likes to work right here, optimum, his optimal, and remember, you have to use the word optimal all the time. Its optimum is at 2. For salivary amylase, its optimum is at 7, and for arginase, its optimum is around 9.5 right here. So each one of them has their own pH. As long as they're working on their own pHs, they're great. But anything before that, below or above that, will cause the enzyme to slow down its work. It drops in both ways. So when it comes to pH, you have to mention that each enzyme has its own pH, and all of them have a specific optimum. Again, 2 things. You have to say that each enzyme has its own pH, and each one has their own optimum. Anything above or below, right? Anything above or below the optimum pH, the enzyme slows down. Again, so above or below, anything that is above or below the optimal pH, enzyme slows down. That's what happens when it comes to pH and how the pH will influence. Here, again, look at the x-axis. It's usually the independent factor, which is the pH, and here is the reaction rate. That means how the enzyme's activity is happening. Now we're going for the third one, which is the substrate concentration. Now, this is a graph showing if there is no enzymes, right? So, for example, if you have one substrate concentration and you have one enzyme, the reaction is going. 2 substrates, 2 enzymes, the reaction is going. 3 substrates, 3 enzymes, the reaction is going. So as the substrates and the enzymes are going, you just keep going that way, right? It just increases. But that's 1 for 1, okay? So as long as there's more substrates and there's enzymes in there, the reaction goes faster and faster. Add more substrates and you have more enzyme, great. The reaction is going faster, more it goes. So it's proportional, right? More collisions, more faster reaction. But as long as what? As long as you have the same amount. So if you have 100 enzymes, there should be 100 substrates. If you have 1,000 substrates, you should have 1,000 enzymes. So if they're walking side by side proportionally, it's just a linear going up like that, and it's just speeding up and going faster reaction. Here's the catch. Now we do have a Vmax. Vmax means there's a maximum capacity. If I tell you that there is only 100 enzymes in your body, okay? So here you have 0 substrates, and if you get to 100 about here, and 1,000 I mean, and then 2,000 and 3,000 and 4,000, you keep going up. It doesn't matter what happens. Once you reach that 1,000, you don't see the reaction going faster. The reaction eventually plateaus. and we see the word plateau, which means it got stable. It settles down. Now, why is that? Why is it that if I add more substrates, it doesn't make the faster reaction? Why does it just goes straight on a line? Why it does not change the speed of the reaction? Why the speed of reaction stays the same? So let's say if the speed here was 10, it would just stay at 10. No matter how many times you put a substrate there, it would just do 10. The reason this, let me explain here on this graph. So imagine you have 100 people, right? You have 100 employees. They work in a company. And then you have 10 clients. Great. You give 10 clients to 10 employees. I'm going to put these in employees. That's awesome. And it's working, right? If I have 15 clients coming in and I have 15, yes, there's more action happening in the company, right? More action. If I put 20 clients, I still have 20 employees. That means more action, right? You can see the action is rising, 10, 15, 20, the action is going faster. If I have 40 people coming clients and I got 40 employees, great, more reaction, more things are going faster. Keep going. That's totally fine. We have 60 clients, 60 employees, more reaction is happening in the company. Great, everything's great. I hit 100 clients, and I have 100 employees. Great. We have reached the maximum capacity of workers in that company, right? But we're really working fast. Everybody's going. Suddenly, I have 115 clients, and I have, 100 employees. I added 15 more clients. Does that mean that there's going to be more productivity in the company? Of course not. What's going to happen to those 15? They're going to sit their butts right there in a chair in a waiting room and wait for one of those enzymes or one of those employees to be free again so I can take him. So did I speed up reaction by adding more 15? No. What happens? I reach my maximum capacity that I can work. So that's why this shows like, oh, one more, there, we got it. Oops, we have the maximum capacity. Now what happens? We go straight line. Because we only have 100 employees, that means the maximum capacity that we can work. And that's what is meant by this graph right here. Like, if I increase the amount of employees, like for example, if I increase here to 1,000, oh, that's great. What is 15? It's nothing. We got 15. We can raise this up more and keep going until we get to 1,000. So it depends on the amount of the enzyme. So it's not about the substrate. You can add substrate as much as you want, but what matters here is the enzyme. If you have enough enzymes, yes, the reaction will keep going. But if you reach the maximum amount of enzymes, no matter what, no matter how many times you add more and more clients or more substrates, it does not make the enzymes go faster. They will just say, sit there and wait, because that's the maximum we can work at. That's what it means by substrate concentrations. So let's get a summary of these three factors and let's work in some ways that we can do experiments about these guys. So the three things that we can do is the temperature, it is the pH, and the substrate. I'm just going to put it as a sub. Now, we also have to know their graphs, right? So for the temperature, we have the temperature in the bottom. For the pH, with the pH in the bottom. And then we have for the substrate. Here we put, I'm just going to put enzyme activity. It can be enzyme activity, okay? Let me write here the whole word. Oops. Enzyme activity. The graph will be something going mountains and then I drop. This one, it can be, you gotta have to show different pHs, like one here, and you can see a pH of 2, and then you have one going like this, a pH of 7, and you can have one going down like this, pH of 9, and this one, it'll be going up, and then it goes straight line. So these are the three graphs. Each one represent. You can get points for drawing these graphs. When it comes to temperature, increased temperature, and the enzyme activity will increase up to what? The optimum temperature. After that, what happens after that? Denature. Also, you can talk about how if you increase in temperature, there is more collisions. So these are 3 points for the temperature. The first point you got was by saying increasing the temperature increases the enzyme activity up to the optimal. That's the second point. This is the first point. This is the second point. And then there's a third point here where, of course, you get denatured. And the fifth point says that if you increase the temperature, more collisions. Some IB mark schemes will not consider these 4 points. They will connect these two together as one, okay? And then this is a second and third. So put all of it. So, and then this will be the 6th point because you draw the stuff. So please write all these. This is just for the temperature, right? As the temperature rises, enzymes arrive up to the optimal. You have to mention the word optimal here. And after that, there's the nature, mention the nature. And if the temperature is rising, that means more collisions. These points, you get it with the graph. Now, when it comes to pH, you will say each enzyme has its optimum pH, right? If above or below the optimum pH, the enzyme denature, right? So above or below the optimum pH, the enzyme denatures. That means the amino acids lose charges. So remember, the amino acids lose their charges because if you change the pH, you change their charges. So that's the nature. Now, and of course, you have the point by drawing the graph. So again, when it comes to pH, each enzyme has their optimum pH, right? Anything above or below will cause it to denature, and that means the amino acids have lost those charges. That's the points that we get for the pH. Okay? And don't forget, draw the graphs. Once again, drawing these graphs, important. But when you draw, you have to put the pH on the X and you have to put the enzyme activity on the Y. If you just do the graphs without showing the X and Y's, you don't get those points. And then, of course, we got the substrate. Substrates, it means for every, for every substrate, it binds to one, let's say one enzyme, and the reaction happens. If there is more substrate, I'm going to put just sub, than enzyme, then the reaction will plateau. So for every substrate, there's an enzyme. If you have more substrate than an enzyme, then the reaction will plateau. You can also add here, they will plateau because there's not enough enzymes anymore. That means we have reached the maximum amount of enzymes. You can add that. You reach the amount of enzymes that can activate. So you do that and you draw this graph and you get for the substrate. So once again, for every substrate, there's an enzyme. If you have more substrates than enzyme, then the reaction will plateau. And that means you have reached enough enzymes working, so you cannot do anything. You have to wait for an enzyme to be free so you can work it again. So these are the 3 factors of pHs. Factors that can affect the rate of enzyme. That means the temperature, the pH, and the substrate. Now, if you had to design a lab, you're going to have to pick one of these 3. So for example, I can put in a test tube, right? I can put, let's say, right here, I put a chicken. Okay? And I put it on a liquid, and inside this liquid, I will put an enzyme that breaks protein. So I can put, let's say, pepsin. Okay? Now, I put pepsin in the chicken. Now, of course, pepsin will break the chicken protein. Now, what I want to do is to see which pH is the best. So I will have right here 5 different pHs. So I can do 1, 2, 3, 4, and 5 different pHs. Okay? And then you can do different too. It can be like 2, 4, 6, 8, 10, as you wish. So these are 5 different types of pHs. And then what I'm going to do is put the chicken and the enzyme on each one. So when I do this, then I'll test to see in which one did the enzymes work the best. But if you do remember, pepsin works best at 2. So this one is going to do the best breaking down. Now, how can you check for how much protein there is? There is different types of equipments that you can use to see the change of color. Like if it gets really dark blue, then you will find out that there is more proteins in there. And if it's less blue, that means the proteins have been broken down. There's one way of doing that. So this you can do by manipulating the pH. But remember, there's these 5 tubes. Each one has to be tested 5 times. That would you do the reaction for this. Another one could be with the temperature, right? When it comes to the temperature, you can get the same thing. You get test tubes. And they all have exactly the same amount of enzyme. So it's a chicken right here, and you have the same amount of enzyme here, enzyme here, enzyme here. The only difference is temperature 10, 20, 30, 40, and 50. And then you check which one has more reaction, like which one breaks down more. And of course, all of them times 5, because you have to do 5 trials for each temperature. 5 for 10, 5 for 20, 5 for 30, 40, and 50. And of course, you put heat here, right? You can heat it up, the liquid, or you can put a Bunsen burner under it and try to see which one comes out. That would have been for temperature. When it comes to substrates, substrates is you can put, let's say, 10 enzymes in here, right? And it's 10 enzymes on each one of the test tubes. 1, 2, 3, 4, 5. Again, 10 enzymes, 10 enzymes. You put the chicken, 1 chicken here, 2 chickens, 3 chickens, 4 chickens, and then 5 chickens. So what did I change here? I changed the amount of substrate, which is who? The chicken. So there was 1 chicken, 2 chickens, 3 chickens, 4 chickens, 5 chickens. What I did, I increased the substrate, but I kept the enzyme the same. Most likely, we might say that here, that 10 enzymes, that's when they were functioning with the 3 chickens. Beyond 3 chickens, then the reaction started to slow down and nothing happened. It just stayed the same. So this is another way. So these 3 are the different ways that you can manipulate the reaction of enzymes by using these straight factors: temperature, pH, and substrates. So with now doing this, now let's talk in real life when we're using enzymes in industry. So first thing, we need to know some properties of the enzyme, which is very important that you know this to write an essay about enzymes. The first and the most important thing, and I already mentioned from the beginning of this video, is that they are catalysts, right? And that means they makes the reactions go faster and easier, which that means you can produce a lot more, right? In a faster pace. Now, the best thing about it is they're not consumed, which that means they can be reused. Every time the enzyme does its job, you can pick him up again and do another one, and you can pick him up again and do another one. So the enzyme doesn't worn out. The enzyme can be reused as much as you want over and over again, which is a good thing. So that means the industries don't have to keep searching for enzymes. Once they have that enzyme, they can use that enzyme again and again and again. Now, the enzymes show specificity for the reaction they control, right? So that means, what if you just want to break down one thing and you don't want to break out the rest? You get that enzyme that will only break that thing and it will not break the rest. So that's why it's great. Enzymes is like, we are very specific people. We only deal with this thing. So yes, I just want you to break this thing. Do not break the rest. So industries and factories, for instance, they can focus on just breaking one thing instead of throwing one thing and then everything else is going. So specificity here, right, it's very important. And the enzymes are very sensitive to the environment, which that means you can manipulate with temperature, with the pH, or the substrate concentration. So factories can play with the temperature, factories can play with the pH and the substrates. They can decide if they want the enzyme to go faster or if they want the enzyme to go slower. So recapping here, the enzymes are catalysts, right? They can be reused 1,000 times. They're very specific, and they can be manipulated by temperature, pH, and substrates. So these are 4 important things that you must remember about the enzymes that you must write on the essay. Now, you need to know an example in the real life factories that use that. And this is the example when it comes to lactase. This enzyme here, lactase, it breaks down lactose. Now, if you remember from carbs, lactose is made of glucose plus, that's right here, galactose. So once you join glucose with galactose, you get lactose. So if you put a lactase here, lactase will break the lactose into galactose and glucose, which is great. So why are we talking about lactase here? Because unfortunately, there's some people who are lactose intolerant. What does that mean? That means they cannot tolerate the sugar lactose, and usually they are found in milk, and some other products like cake and stuff, right? That has milk in there. So when these people eat food that has lactose, they have digestive problems, right? So what do they get? They get nausea, cramps, bloating, gas, diarrhea. Only because they don't have the enzyme lactase. So imagine, every time they eat food that has this sugar lactose, they get nausea, cramps, bloating, gas, and diarrhea. So they only have two options. One is check every food that you're eating and make sure that food doesn't have the sugar lactose. Because it's fine, right? If you don't eat lactose, you don't have to worry about breaking it down. But if you like that ice cream, if you like that cake, if you like to drink cornflakes with milk, you're screwed. You want to do that. But you don't have the enzyme lactase to break this guy lactose. So what do you do? What if I drink a pill that has this enzyme lactase? Or what if I make the food that breaks down lactose before I can even eat? That's the whole point of the factory. So they produce tablets or pills that has lactase enzyme. So some people, they take the pill lactase and then they drink the milk. So by them having the enzyme inside their body, they're able to break down that milk. Or they can have a special lactose-free diet if necessary. So here's the reaction, right? You have lactose as substrate, the enzyme is lactase. Lactose with water, by the enzyme lactase breaks the glucose and galactose. This is a hydrolysis reaction going back to 2.1. Now, what do? They take an enzyme from this enzyme here, lactase enzyme, which is beta-galactosidase. Now it's taken from a fungi known as Aspergillus oryzae, which you do need to know that it's from a fungi. So here's what the industry do. They took that fungi, and inside that fungi, they took the enzyme lactase, okay? Now that they have the enzyme lactase from the bacteria, what do? They create these beads right here. Each of these beads right here is made of lactase, okay? Now, they have a milk that contains lactose. It contains that sugar lactose. So the milk is coming here with lactose. But as this milk is passing through these beads which has lactase, what's coming out here? It's coming here glucose and galactose, right? It's breaking it down. So what does that mean? You don't have lactose anymore. They already have been broken down to glucose and galactose. So you're completely fine. When they do that, they can produce lactose-free products. That means you can have ice cream without lactose. You can have cake without lactose. Why? Because they broke down that lactose in the milk before they made that ice cream, before they made that cake, so those people can actually eat. That's why you go to supermarket and you see lactose-free milk and lactose-free blah, blah, blah. Is because these products have gone through these beads of lactase in which the lactase broke it down into glucose and galactose, and now those people eat. Now, what if you end up in a restaurant where they don't have anything that is lactose-free? Then that person has to make sure they have a pill, and that pill has lactase enzyme. So they take that pill and then they eat, and since now they have the enzyme in their body, they're able to break it down. Now, one last thing that before I forget is that every time you have lactase breaking down these lactose, they become more sweet. So all these lactose-free products, if you drink them, you will notice the lactose-free products are more sweeter than the milk that has lactose. It's just because you have produced a lot of glucose and galactose. So if you had to write an essay on this, it is extremely important that you mention the reaction right here. Let's highlight lactose and water by lactase glucose. That's a point. Just mention the lactase, the enzyme is breaking lactose into glucose. You also mentioned that it came from a fungi, the enzyme. You mentioned about the immobilized enzymes here. Immobilized means they're on place, they're not moving, but they're being reused again and again. So you can mention how they're used in the factory to break down the lactose from milk, and that means they produce free products of lactose-free products. And these lactose-free products are very sweet. And what do these guys do? they stop people who are lactose intolerant from having nausea, cramps, bloating, gas, and diarrhea. That's how you get the points for talking about enzymes in the industries and lactose-free and lactose intolerance and all this stuff. And that's pretty much for this topic 2.5 on enzymes. Here are the questions in the study guides. You can always go back to the videos and find the answers to these questions, as well as these questions right here. And thank you.